Okay, so we will take a look at using the Metropolis Algorithm, MCMC, as a way to, I guess, decipher some classical, I don't know, like very basic cryptography stuff, okay? So what we mean by, we're going to take a look at what we call substitution ciphers. So, I don't know, I felt like, I guess it depends who you were as a kid, but if you were into like, there might have been a phase in 4th grade when you were into like secret messages and you would come up with little codes and you would have some kind of decoder thing, you know, and you would write these things, and then, you know, the novelty wore off because it was, you had nothing very important to say as a 4th grader, and it took 10 minutes to write a message. But you know, perhaps perhaps the history of this problem arose when you know, kind of these jailers found that their inmates were passing these encoded messages, and you know that you're not supposed to do that when you're in jail, and they wanted to know what was the contents of the message because, you know, maybe, you know, you might have something important to say. Okay, so the classic a substitution cipher, you know, works like this. You have A, B, C, D, E, F, G, etc., etc., etc. Okay, X, Y, Z. And then you just you mix up the letters and you say, I'm going to say now A is now the letter N, and B is the letter J, and C is the letter X, and D is the letter P, and basically you just shuffle the 26 letters here. Yeah. And so every letter is substituted with another letter, and that's how the substitution cipher works. So you know, we have this is like very basic, right? Or you know, in the prison secret message thing, you know, they had little you know, they had little symbols here, right? And I don't know, something like that. Okay. You guys know the Pigpen cipher? Oh man, you guys are missing out. What's that? Oh, Raiders. Oh yeah, yeah. Oh yeah, Raiders of the Indiana Jones ride at Disneyland. It's a substitution cipher with all of these things. They give you the key. Okay. I should not waste your time with the Pigpen cipher, but you can look it up here. This is it right here. A, B, C, D, E, F, G, H, I. Okay, and then so if this is your, let me copy image and we'll paste this here. So this is an, oh, that's not correct. This is an example of another substitution cipher, except you're just not using letters. You're using these shapes here. Shapes, I'll show you. Okay, so I shrink this down. Okay, and then so the letter, if you wanted to write hello, from here you would do H, because the H is right there. The E is the box. The L is this, and then the O is this. Okay, that's the Pigpen cipher in it, and it looks, you know, when you see this, it looks very cryptic, but it's just a simple substitution cipher. Okay, and basically you're just putting in letters for each thing here. Okay, so this is a simple substitution cipher. Just each letter. Stats 102C. What is this? Week 7, Friday. Okay. So each letter is replaced with another one. That's basically it. Okay, what we're going to do is, let's say you get some kind of something that looks like this. This is a substitution cipher, and what we want is we want to figure out what is encrypted here, okay? And here it took us about 2,200 iterations, but we figured out that the first line is the Project Gutenberg ebook of Oliver Twist by Charles Dickens, okay? But with a substitution cipher in the beginning, it looks kind of like this. All right, how did we decrypt this into this, okay? Well, this is going to be done via, believe it or not, the Metropolis algorithm and a little bit of an optimization rule. Okay, so we're going to use the Metropolis algorithm to kind of, propose and, whether we accept or we don't accept a new thing. And then, I don't know if you guys took 102B yet or not, but we're also going to try to optimize kind of this, like the likelihood of our text here, okay? And so, you can read all of this stuff here. And okay, and so they've formalized a lot of the things that we've been talking about in the thing, and basically what we're going to do is we're going to have to try to measure certain kind of combinations of letters as a way of probability. Okay, and this part gets a tiny bit complicated, but we need a way to measure, and we'll discuss this next week. Okay, so we will find a way to measure the probability of a given cipher. Okay, a cipher being, we'll define a cipher as, a matchup between the letters A through Z to another set of, another permutation of the letters. Okay, so a cipher will be basically a quote solution key. And so someone can say, oh no, this is the solution key. A through Z is matched up to these letters, and then someone else can say this solution key is better. And so we're going to need a way to measure the probability of a given cipher. And then so once we have that, then we can use the Metropolis algorithm, because we can talk about the probability of the proposed cipher versus the probability of the current cipher. Okay, so we're going to look at kind of the, so we'll have a way to measure the basically the probability of the proposed cipher divided by the probability of the current cipher. All right, and so we'll have to talk about this, and then the idea here is we're going to just run the Metropolis algorithm. Okay, so we propose a cipher, and the cipher that we have to propose, because it's the Metropolis algorithm, it needs to be what we call a the proposal needs to be symmetric. Okay, so we propose a cipher, and then we find the probability of moving, which is equal to min of 1 p proposed divided by p current, and then we move or not move. Okay, And so let's think about why would something like this work, okay? So if you think about what is the space of all the possible values that the proposed thing can take, okay? There's a lot, right? There's basically 26 factorial arrangements, okay? 26 factorial ciphers, right? There are, what is that equal to? Is that what is that on the order of? 26 factorial? Oh no. Wait, how do you do factorial? This factorial. Okay, so it's on 4 times 10 to the 26th power. Okay, it's on. This is a very big number, right? Okay, so this is too many for us to try to manually try all of these. Okay. However, we have to think. The way, I don't want to get into the way we're going to measure the probability here, but basically we're going to just look up for either kind of common word, like letter combination patterns and word patterns, okay? So we will look at, look for, common word pattern / letter combos. So basically, if you see the letter Q, what's almost certainly going to be the letter that comes after? U, right? Okay. I mean, sure, you could have other things, but basically, if Q, then probability of U will be, like 0.99 or something like that, right? I don't know. I'm making that up, but it's going to be high. Okay. And meanwhile, if you have the letter B, okay, then there are lots of possibilities, like A, E, I, O, U will all have high probabilities. R will have a high probability, and L and I don't know what other letters, right? But X will have, these will have high probabilities. X will have a low probability, K and N and Z, and there's a bunch of letters that we would say these letters should not come after the letter B, right? So we can kind of start establishing sets where we can start to measure a little bit, what makes sense and what doesn't make sense, right? So when we start to see the deciphered text, we can, if we see BX and BK as part of the words, we're going to be like, man, this doesn't seem quite right. Whereas, so if I don't know, you have you might have two sets of possibilities, right? Let's say this is our deciphered this is our encoded text, and after you decipher it, one possibility is we'll say this, and another possibility is right, and neither of these are going to be correct, but one seems more correct than the other, right? So this is, this is not correct, but more likely, and this is not correct and less likely. Okay, because certain things will start to, form certain patterns. Okay, so we'll get into this next week. But and so you have to think of the possible ciphers, the distribution. If somehow we were able to look at the distribution, most of the possible ciphers, if we were able to like list them out, and this is where if we could list off all 26 factorial ciphers, most of them are going to have probabilities very close to 0, right? And then there will be like just a few ciphers where the probability is reasonably high, okay? And perhaps you just have a few letters mixed up, like where, you know, one is the correct cipher and then another one is just a small variant of the actual correct one. The correct one will probably have the highest probability, the correct cipher, and then the other ones that are very similar will be, you know, identical to the correct cipher, except, you know, maybe we switched the letters C and L or something like that, you know, or L and R or something. You know, we switch some combination of letters where, you know, we're not getting exactly English, but something that looks pretty close to English. Okay, and that's why, you know, when you look at the example here, it moves into things that look, it is completely gibberish, and then it's trying to establish things that look a little bit more readable, right? Like this is not anywhere near real English, but it kind of feels like it could actually be some language here, right? And then, you know, as it gets better and better, as we get closer and closer, you know, this is pretty close, okay? Except it's got an S instead of a T here, and so, you know, and it's not the Project Gutenberg, it's She Projects Gutenberg, and so it's not quite correct, but it's pretty. It feels somewhat right, even though it's wrong. And then until, you know, we get to the spot that we're looking at, okay? And so, you know, our symmetric proposal, the way, you know, we will propose, and this seems totally ridiculous, but this is how we're going to do it. What we do is what we propose is we just take the letters and we just swap two random letters. So maybe we start off with A, B, C, D, E, F, G. So we'll just swap E. Okay, we'll just swap D and L. Okay, et cetera, et cetera, et cetera. And if we think about it, you know, this is, you know, we start off with this cipher where we say the letter A corresponds to A and B corresponds to B, and it, you know, it gives us gibberish, and then we swap this, and then so now we have A, B, C, L, E, F, G, you know, H, I, J, K, D, M, N, O, P, and then we plug this into our thing, and we say, okay, does this produce something that's a little bit more readable or less readable? Okay, and so this will be kind of our proposed thing. This is it's a symmetric proposal because if we currently have this, we are just as likely to propose this as, you know, from here we were to propose this, because we're just taking two letters and we're just swapping them. And so to go from one to the next, you have a symmetric probability of, you know, we are just as likely to propose this as we are to propose in the other direction. So if this is our current state, you know, we ask, you know, what are we going to propose next? We can propose all sorts of things. It's just as likely to propose this one as it was to propose this way. Okay, so the probability of proposing is symmetric. So that works as our Metropolis algorithm, and what we do is we're going to just keep swapping these things, and if the proposed swap is totally garbage, we are not likely to accept it, or, you know, we might accept it with a low probability. Okay, and on the other hand, if by random chance we happen to do a pretty good swap, like we swapped the letter E into a place where a vowel goes, that's going to increase the probability of that cipher, right? That the cipher there is there. And then so if that with the Metropolis algorithm is if the proposed probability is higher than what your current is, you're going to move there. Okay, and then so now you're at this new spot, and then you just keep proposing new swaps. And if that proposed probability is higher, then we keep moving in that direction. And so I'll have to work on coding this up. So the two things that I'm having you guys read, one is it's a little bit more technical. This one's that's this paper here. It's pretty good. And then the other one is an excerpt from this book called Machine Learning for Hackers. I think it's like a sensational title. It's not that amazing, but it does do an example, and they have code written out here. So be sure to read those. I think this is kind of a neat example.